Welcome to The Explainer. This one's proudly brought to you by Forge College. So today we are finally diving into a super exciting phase of our journey, the capstone project. We're going to take all those artifacts we built in the integration checklist lesson and actually translate EVM token logic straight into Solana's high-speed architecture. If you've been sitting there wondering how on earth to map out a token strategy without, completely pulling your hair out, well, you are in exactly the right place. Let's get into it.
All right, here's our blueprint for today. First, we'll tackle the Solana mental model. Then, mapping the ERC standards. Third, the four-stage workflow. Fourth, translating token allowances. And finally, devnet tests and success. Starting off with part one, the Solana mental model. You see, porting tokens from Ethereum to Solana isn't just about swapping out a few lines of syntax. Oh no, it is literally like translating a complex novel between two totally different programming languages. Before we even think about writing a single line of code, we really have to fundamentally rewire how we think about state and authority. Okay, think about it like this. Over in EVM land, a smart contract is basically this giant, super heavy cardboard box. It's kind of like a digital episode of Hoarders. Every single thing is just stuffed inside it, your logic, the variables, the user balances, the whole shebang. But on Solana, it's the exact opposite. Solana takes that state and spreads it around like confetti across different independent accounts. You've got your programs holding just the logic, separate mint accounts tracking the overall supply, and specific user accounts holding the actual balances. It's highly modular, it's distributed, and honestly, that's exactly why it's lightning fast. Now, since we're no longer hoarding all that data inside one single contract box, we obviously need a way to manage authorities securely, right? Well, enter the program-derived address, or PDA for short. You can think of a PDA as this special account that is strictly controlled by a program's logic rather than, say, a user with a private key. When you're trying to handle things that an EVM contract would normally just do internally, like pausing a token state or tracking allowances, PDAs are going to be your absolute best friend. Seriously, you'll use them everywhere. Moving on to part two, mapping the ERC standards directly to Solana primitives. Now that we've got our mental model tuned to this whole distributed state and PDA concept, let's grab our schematics and actually map out some specific everyday ERC responsibilities to their brand new Solana counterparts. It's actually kind of amazing how cleanly these two worlds align, as long as we stay disciplined. For instance, ERC minting, that maps perfectly to a mint account or a PDA on Solana, which we'll test by attempting both authorized and unauthorized mints. What about EVM balances? Those map to associated token accounts, and we test them just by doing standard token transfers. And EVM NFT metadata? That whole chunk moves over to Metaplex token metadata accounts, which we verify by actively mutating the data. The big takeaway here is that every single EVM function gets a specific new home, and naturally, a verifiable devnet test to match. Now, speaking of those ATAs, let's make sure we are crystal clear on this one, because it's a big deal. An associated token account is the exact deterministic account where a user's actual token balance lives. Unlike an EVM ledger, where your wallet is pretty much just mapped to a random number in a giant dictionary, Solana requires these specific, distinct accounts for tracking who owns what. Bottom line, if you want to hold a specific token, you absolutely need an ATA for it. No exceptions. All right, part three, the four-stage workflow and our project execution plan. We've got the vocabulary down, we've got our mapping matrix, so let's break this massive capstone project down into a highly pragmatic workflow. We definitely don't want to end up lost in the engineering weeds here. So, here is exactly how our execution plan is going to unfold. Step one is discovery. This is where we take the gap analysis from our previous lesson and finalize our whole architecture on paper. Step two is the prototype phase, where we build out minimal anchor handlers and make sure they pass local unit tests. Step three is the devnet deploy. We push to the live test network and just hammer it with edge cases. And finally, step four is documentation, where we neatly package up our verified transactions, our code, and all our migration notes. Guys, I really cannot emphasize this enough. Every single stage of that workflow has to produce a very specific triad: code, tests, and documentation. Adhering strictly to this trio is literally your best defense against the dreaded scope creep. Think about it. If you write a bunch of code without a corresponding devnet test, you haven't actually proved that your mapping works. It's truly that simple. You gotta have all three. Which brings us to part four, translating token allowances and bridging the SPL gap. Let's tackle a very specific, real-world translation challenge that trips up, well, almost every single EVM developer making the jump to Solana. So here's the million-dollar question. How exactly do we handle ERC-20 allowances on Solana? On Ethereum, allowances are super standardized, right? You just call approve and walk away. Easy peasy. But the native SPL token program, it doesn't actually have a direct one-to-one native equivalent. It's a pretty major architectural friction point, which means we actually have to step up and engineer a custom solution. But hey, thankfully we aren't flying blind here. We have 3 really solid emulation strategies to pick from. Option 1, use program-owned PDAs to just manually store those allowance records. Option 2, rely on off-chain signed permits, kind of similar to EIP 2612, where the user signs a message for the program to verify later. Or Option 3, use Solana's native delegated token accounts. The strategy you end up choosing here is going to directly dictate exactly which devnet tests you need to write in the next phase. And that leads us nicely into part 5, devnet tests and success. This is the grand finale. How do we objectively prove our translation was a resounding success? Because look, success isn't just saying, hey, it compiles. Success is actually executing this devnet checklist. We need concrete proof. We must test unauthorized mints to prove our authorities are fully secure. We have to verify our ATA transfers. If we ported over a paused state, we need to validate that transfers actually fail when the system is paused. For NFTs, we've got to actively mutate Metaplex metadata and test freeze behaviors. And oh, if you're porting over security tokens, you'd be rigorously testing your KYC claim flows right here too. Listen, if you take away nothing else from this entire explainer, please remember this core principle. Always separate authority responsibilities from account storage when you're mapping ERC semantics to Solana. On Ethereum, like we talked about, they are just totally mashed together in that heavy cardboard box. But on Solana, keeping who can do what strictly separated from where the state lives is literally the ultimate secret to building clean, hyper-performant SVM architecture. So, what do you think? Are your artifacts and tests ready to map explicit anchor patterns? More importantly, now that you've dismantled that clunky EVM cardboard box, are you ready to harness the true speed of distributed state? In our next lesson, we're going to roll up our sleeves and start building out those handlers. Thank you so much for joining me for this explainer, proudly brought to you by Forge College. I highly encourage you to go visit forge.college to continue your Web3 journey with us. Until next time, happy building and stay curious.